Grounding the antenna or tower is crucial for safety and protecting equipment. Several materials are needed. Firstly, ground rods, which should be 8 feet or longer. Secondly, ground wire consisting of stranded copper wire, sized at number 6 American wire gauge or larger. Thirdly, ground clamps are needed to secure the ground wire. Fourthly, a bonding strap is required for connecting the ground rods together. The procedure involves several steps. Firstly, install the ground rods by driving 2 or more into the earth, at least 8 feet deep and spaced 6 to 8 feet apart. Secondly, connect the ground rods using a bonding strap to securely join them. Thirdly, run a copper ground wire from the bonding strap to the tower or antenna mast. Fourthly, attach the ground wire to the tower or mast using a ground clamp to ensure a solid connection. Fifthly, test the grounding system using a grounding tester to verify that it is properly grounded. An antenna discharge unit, or ADU, is installed on the main lead to provide protection against lightning damage. Section 810.21 of the National Electrical Code, or NEC, provides guidelines for grounding electrical installations. The messenger cable in RG6 60% messengered cable can serve as a ground path for the main lead if it is properly bonded to the grounding system. Ensure the messenger cable is connected to the tower or antenna mast using a ground clamp. Use corrosion-resistant materials for all grounding components to prolong the lifespan of the installation. Inspect and maintain the grounding system regularly to ensure its proper function. It is wise to consult with a qualified electrician for any complex or large-scale grounding installations. By following these steps, the safety and integrity of the wireless cable system can be helped, and minimize the risk of damage from lightning or other electrical hazards. Grounding systems are designed to provide a low-impedance path for fault currents to return to the source. This helps to ensure that overcurrent protection devices, such as circuit breakers or fuses, will operate quickly and effectively to clear a fault. A properly grounded system also helps to minimize the risk of electrical shock to people who may come into contact with electrical equipment or conductive surfaces. In addition to protecting people and equipment, grounding systems can also help to reduce electrical noise and interference. This is especially important in sensitive electronic equipment such as computers and communication devices. The size of the ground wire used in a grounding system is determined by the size of the circuit being protected. The National Electrical Code, or NEC, provides specific requirements for ground wire sizes based on the amperage of the circuit. It is important to follow these requirements to ensure that the grounding system is adequate to handle the potential fault currents. The type of ground rod used in a grounding system can also affect its performance. Copper ground rods are a popular choice because of their excellent conductivity and resistance to corrosion. However, other types of ground rods, such as galvanized steel or stainless steel, may also be used depending on the soil conditions and other factors. The depth to which a ground rod is driven into the earth is also important. The NEC requires that ground rods be driven at least 8 feet deep to ensure that they make good contact with the earth. In some cases, it may be necessary to drive ground rods deeper to achieve the desired grounding resistance. The spacing between ground rods is also a factor to consider. The NEC recommends that ground rods be spaced at least 6 feet apart to minimize the interaction between their grounding fields. In some cases, it may be necessary to space ground rods further apart to achieve the desired grounding resistance. The bonding strap that is used to connect ground rods together should be made of a conductive material such as copper or aluminum. The bonding strap should be sized appropriately to handle the potential fault currents. The ground clamp that is used to attach the ground wire to the tower or mast should be made of a corrosion-resistant material such as copper or stainless steel. The ground clamp should be designed to provide a secure and reliable connection. A grounding tester is used to verify that the grounding system is properly installed and functioning correctly. A grounding tester measures the resistance between the grounding system and the earth. The resistance should be low enough to allow fault currents to flow easily back to the source. If the resistance is too high, it may indicate a problem with the grounding system. An antenna discharge unit, or ADU, is a device that is designed to protect electronic equipment from damage caused by lightning strikes. An ADU typically consists of a gas discharge tube or other surge suppression device that is connected between the antenna and the equipment being protected. When a lightning strike occurs, the ADU diverts the surge of energy to ground, preventing it from damaging the equipment. Section 810.21 of the National Electrical Code, (NEC), provides specific requirements for grounding antennas and satellite dishes. These requirements are designed to ensure that antennas and satellite dishes are properly grounded to protect people and equipment from electrical hazards. The messenger cable in RG6 60% messengered cable can be used as a ground path for the main lead if it is properly bonded to the grounding system. The messenger cable is the outer conductor of the coaxial cable. To use the messenger cable as a ground path, it must be connected to the tower or antenna mast using a ground clamp. It is important to use corrosion-resistant materials for all grounding components to prevent corrosion and ensure that the grounding system remains effective over time. Corrosion can significantly increase the resistance of the grounding system, which can reduce its effectiveness. It is also important to inspect and maintain the grounding system regularly to ensure that it is functioning properly. The grounding system should be inspected for signs of corrosion, damage, or loose connections. Any problems that are found should be corrected immediately. For complex or large-scale grounding installations, it is always best to consult with a qualified electrician. A qualified electrician will have the knowledge and experience to design and install a grounding system that meets all applicable codes and standards. By following these steps, the safety and integrity of the wireless cable system can be ensured and minimize the risk of damage from lightning or other electrical hazards. Grounding is a critical aspect of electrical safety, and it is important to understand the principles of grounding to ensure that electrical systems are properly installed and maintained. Additional information to discuss grounding systems in more detail. Firstly, the purpose of a grounding system is to provide a low impedance path for fault currents to return to the source. This helps to ensure that overcurrent protection devices, such as circuit breakers or fuses, will operate quickly and effectively to clear a fault. Secondly, a properly grounded system also helps to minimize the risk of electrical shock to people who may come into contact with electrical equipment or conductive surfaces. Thirdly, in addition to protecting people and equipment, grounding systems can also help to reduce electrical noise and interference. This is especially important in sensitive electronic equipment, such as computers and communication devices. Grounding electrodes are used to connect the grounding system to the earth. The most common type of grounding electrode is a ground rod, which is typically made of copper or galvanized steel. Ground rods should be driven at least 8 feet deep into the earth to ensure that they make good contact with the soil. Grounding conductors are used to connect electrical equipment to the grounding system. Grounding conductors should be sized appropriately to handle the potential fault currents. The size of the grounding conductor is determined by the size of the circuit being protected. Bonding is the process of connecting all metal parts of an electrical system together to create a common ground potential. Bonding helps to prevent voltage differences from developing between different metal parts, which can reduce the risk of electrical shock. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock. GFCIs monitor the current flowing in a circuit and quickly interrupt the power if a ground fault is detected. Ground faults occur when current leaks from a circuit to ground. Surge protection devices, or SPDs, are devices that are designed to protect electrical equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, power outages, or other events. SPD divert the surge of energy to ground, preventing it from damaging the equipment. The National Electrical Code, or NEC, provides specific requirements for grounding electrical systems. The NEC is a set of standards that is designed to ensure the safety of electrical installations. The NEC is updated every 3 years. Grounding systems should be inspected regularly to ensure that they are functioning properly. The grounding system should be inspected for signs of corrosion, damage, or loose connections. Any problems that are found should be corrected immediately. Proper grounding is essential for electrical safety. By following the guidelines in the National Electrical Code, or NEC, and by inspecting and maintaining grounding systems regularly, it is possible to minimize the risk of electrical shock and protect electrical equipment from damage.